episode 88, Galaxy Munchies. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart. Sitting opposite me at the table in her office, Dr. Emily Brunsden. Emily, hi, how are you doing?
Hello, hello. I'm doing very well, thank you.
Good. Did you manage to see a lunar eclipse this week?
It turns out I live in the wrong place, really.
Yeah. Well, I mean, wrong place for a couple of reasons. It's been really cloudy all this week, so we wouldn't have seen it anyway, but it was only a southern hemisphere thing, is that right?
No, it's to do with longitude rather than latitude, right. So we're at the wrong...
We're wrong time.
Yeah.
Right, potentially right place, just wrong time.
Yeah, wrong time zone. So it sort of started happening as the sun was rising here in the UK, so we didn't really... catch
which is not what you want for a lunar eclipse.
No.
But apparently it was the longest one or something. It was an impressive one.
Yeah, they always pick out some sort of random stat.
It was the biggest one that you could see from the window of your house. I don't know, something. Yeah, I did see a lot of social media from people I know down in Australia who were up at the right time in the right place, but there were lots of clouds. Seemingly everywhere. So I didn't know anyone who got a really good look at it. But do you?
Ironically, in New Zealand, the land of the long white cloud, my parents actually saw it fine. So they said it was really lovely.
So the long white cloud had just sort of shifted for a minute and gone, there's the moon, and then back again. But they got a good view of it.
They did. They did.
And a lunar eclipse, so this is different to a solar eclipse. Just remind us what a lunar eclipse is.
So a lunar eclipse is
It's our Syzygy. There we go. Had to get that one in. Well done. That's twice we've used the bell in the last couple of episodes. Well done. And a Syzygy is, of course, an alignment of three celestial objects. So what's the alignment this time? It's not where the moon gets between us and the sun.
Nope.
It's where we get between the moon and the sun.
Exactly.
And the moon goes into our shadow.
That's exactly right. Yes.
Right.
Yep,
okay.
Yep.
And so the moon just looks really not as bright. Like it's big full moon, but then it's not so bright anymore as it goes into the shadow and goes kind of red.
Yeah. So the difference between a solar eclipse and a lunar eclipse in terms of the amount of light that's illuminating the thing that's in eclipse is that, of course, the Earth has this big extended atmosphere that is very nice for us to breathe every day. But what happens is light is able to pass through and bend from that. So the moon never goes completely dark as you would expect kind of in a perfect shadow. There's still some light reaching it. But that light having gone through our atmosphere is very, very good at scattering blue light, which is why the sky is blue. So we get a preference of red light, which is still traveling in a straight line. Hence the moon looks a bit red.
Right. So it's sort of in perpetual sunrise or sunset as it's going through that shadow. It's all very red, which is pretty amazing when you see it. I remember seeing a really good one when I was living in Toronto many years ago, and it really was a really just blood red thing in the sky. It was kind of scary, actually. We're not going to make it through this night, but everything was fine. Everything was fine in the end. So that was kind of cool. So if you saw that and you want to send us a picture of it, because I'm kind of jealous we didn't get to see it here, send it through to us at syzygy.fm. You can send it through the hello on the webpage there, or through the Twitters, through the Instagrams, all of those sorts of things. Get in touch is what I'm trying to say. But that's not what we're here to talk about today. We're not here to talk about lunar eclipses. We're here to talk about galaxies eating each other, which is a cool topic by anyone's stretch of the imagination. Emily, what's been going on? Who's been eating what?
Yes, well, galaxies are actually very, very famous for doing this. That's a proper scientific word we've got called galactic cannibalism.
Which is, again, it's in that category of you go to a party and someone says, what is it that you do? Well, I research galactic cannibalism. You're on free drinks all night, right? That's going to keep you quite satisfied all evening. So tell us about galactic cannibalism.
So galactic cannibalism is when two galaxies sort of merge, or more likely a bigger galaxy kind of consumes a smaller galaxy. Now, we know that this happens fairly regularly in our universe. Galaxies are not super far away from each other on average, right? I mean, even our own nearest neighbor galaxy, at least the nearest neighbor big galaxy, the Andromeda galaxy, is really not that far away, right? So it's nice and close. So galaxies tend to be much closer, at least relatively, than, say, individual stars are within a galaxy.
Right, okay. So on that scale, if you think about how far stars are apart within a galaxy, there's a lot of distance, and the two stars bumping into each other is pretty unlikely. Whereas two galaxies merging, crossing paths, does that happen all the time?
Yeah, basically.
Yeah?
Yeah.
Cool.
And again, cannibalism of eating smaller galaxies, big galaxies eating smaller galaxies happens all the time as well.
Right. So, but we're not just talking about this in the abstract. There's a point to this, and that point is this has happened?
It has happened, and what's been really exciting is we're normally looking at galaxies, very large galaxies like the Milky Way that are or have consumed smaller galaxies, the satellite galaxies, like, for example, the Large Magellanic Cloud, which is one of the satellite galaxies of the Milky Way. What's different here is that new research has shown that the Large Magellanic Cloud, the small satellite galaxy, has in the past itself cannibalized an even smaller galaxy.
So this is a galaxy which is a satellite galaxy for the Milky Way, having eaten its own satellite galaxy and cannibalized that in the past. So we've got galaxies which have gone then eaten galaxies which are then going around other galaxies. It's galaxies all the way down.
It is, yeah.
Would the smallest of those galaxies have had its own satellite galaxy? When does it end? When does the madness end, Emily?
Well, this is actually a really big topic in galaxy research. It's all linked to how do galaxies actually form in the first place, and it's starting to put some more information into those kind of models.
Right. Okay. So let's back up a little bit. First of all, who's reported this? Whose research are we talking about today?
So we're talking about a group which is led by Munchies in Bologna in Italy.
Very nice.
Yeah, there's a team there who've been looking at globular clusters in the Large Magellanic Cloud. Now, it's worth noting at this point what a globular cluster is.
You're just reading my mind. I was about to ask what makes a globular cluster.
Because otherwise the rest of it's not going to make a lot of sense.
Yeah, we should start with that perhaps.
Absolutely. So a globular cluster is a really tight, dense, pack cluster of stars. So we're talking about usually at least a few thousands, but more up to kind of hundreds of thousands to millions of stars, all grouped together in kind of this spherical distribution.
Now, is this itself a galaxy? Like, it kind of sounds like you're describing a galaxy here.
I guess it's not a galaxy because it's a cluster. It's much smaller in scale. To go to a galaxy, you're really talking about more than millions of stars. You're getting up to billions.
Okay,
right?
So this is potentially a structure within a galaxy.
Yes.
Right.
Well, we'll get to that. But yes. But yeah, so all these star clusters, that's kind of the family of, and we have different types of star clusters, but globular clusters are these quite big, quite densely packed clusters, and also very, very old objects. So the oldest objects that we have found in the Milky Way are globular clusters. So there's some interesting evolutionary things that are going to come back from that observation. But anyway, so we started looking at, now the Large Magellanic Cloud, just like lots of other galaxies, including our own, has lots of these globular clusters within it. So I think we know about sort of nearly 200 globular clusters that are in the Milky Way galaxy, and that's just that we know of. There's heaps more there. Even in the Large Magellanic Cloud, we know of maybe 60 or more individual clusters. So what this team decided to do was actually start to look at in quite a lot more detail of how these globular clusters are composed. So they've got stars in them, and actually what is the metallicity of these stars?
The metallicity, as in what are they made of?
Yeah, exactly. What is their chemical composition? Because that can be a little bit of a fingerprint to tell you actually where this particular cluster was originally born.
Okay.
So we already know, for example, that the globular clusters in the Milky Way have more metals, or what we say, more metal-rich than the globular clusters in the Large Magellanic Cloud.
Now, this is metals in the astronomical definition, right? As
Yes.
in everything that isn't hydrogen or helium.
Yeah.
Is that right? Yeah.
All that other stuff.
To everyone else, all the chemists and the physicists, metals mean something very specific. But to astronomers, it's not hydrogen or helium. It's the rest of the periodic table, which is okay, fine, as long as we know where we stand.
Yeah. And so that tells you sort of, it could be one of two reasons why you might have more or fewer metals in your globular cluster. The first one is you could be older. So if you're talking about, say, the Milky Way galaxy, when we go back to the earliest history of the Milky Way galaxy, there just weren't many metals around. And the reason is you require stars to have gone through a huge bit of their life cycle. So remember, everything apart from hydrogen, helium, a tiny bit of lithium that were formed in the Big Bang everything else that has come from stellar evolutionary processes, effectively. So you needed stars to be born and then to die and then to eject all this material back out.
So if you can look at the composition in terms of, metals and not metals in the astronomical sense, you can get a sense for, well, if there's a lot of the heavier elements, if there's a lot of the metals, then that tells you something about how many iterations you've been through of those stellar life cycles. The only way that you would get anything which isn't basically hydrogen and helium is if stuff's happened over various iterations of lives of stars being born and dying.
Yeah, exactly. Yeah, so it tells you something about the age, and it also tells you something about the location in which they were formed. Because again, if you've got a location in the universe or in a galaxy where you've got lots of metals kicking around, then you're going to have lots of metals in your globular cluster.
Right, that makes sense.
Yeah, if there's less around, then you have less in there. So there's kind of those two factors. There's age and actually what the environment was like when they were formed. So if we go to look at the Large Magellanic Cloud, now this is a satellite galaxy of the Milky Way. Mm-hmm. It's on the larger end of what we'd call kind of the smaller satellite galaxies. So it's actually the biggest one that we have, for example.
How many satellites does the Milky Way have? Like order of magnitude?
Loads.
Is it a couple or is it loads?
It's tens at least.
Right. Okay.
Yeah. So lots of little ones. We don't necessarily know about all of them because they can be incredibly faint. They can be very sparse, which makes them very hard to identify as well.
It's a weird thing. I would have thought that'd be pretty obvious. Like if your galaxy's got another galaxy going around it, you'd see it. I would have thought, but apparently I'm wrong.
Well, yeah, I mean, they're faint, they're sparse, and some of them are just on the other side of the galaxy. So.
Right, it does make it a bit difficult to see them. Yeah. But tens of them, and the Large Magellanic Cloud, it's kind of in the name, it's one of the bigger ones.
Yeah, exactly. Okay. Yeah. So this Large Magellanic Cloud is, to give you a sense of scale, it's kind of about 100th the mass of the Milky Way.
Okay, so it's a lot smaller than our galaxy, but that still can have a lot of stuff in it.
Exactly, yeah. So we're talking about then the clusters. In this study, there were 11 globular clusters that were studied, and 10 of them were very, very similar in terms of their metal content.
So that's all sounding very, very normal. That sounds, fits a pattern.
Basically, they were all formed kind of around about the same time as the Large Magellanic Cloud itself was formed. They're all slightly poorer in metals than the Milky Way itself because the Milky Way just had more stuff around, therefore more star formation, more generations of stars, more metallicity. But broadly, it's kind of telling you the same story that we would expect.
Sure. So that all fits together. One big jigsaw puzzle. Fine. No problems there. That's 10 out of 11, you said?
Well, exactly.
Yeah. So the 11th is fitting the same pattern. It's all very normal and fine and everyone goes home.
No.
Okay.
No.
What was
the 11th is the exciting one.
Yeah.
So the 11th is a globular cluster which is called NGC 2005.
Catchy.
Yeah. And this is one that's different. So it's in terms of kind of globular cluster, like what you would expect, it's actually fairly standard. It's got something like 200,000 stars in it, which is kind of normal. It's quite close, roughly, to the center of the Large Magellanic Cloud. It's a bit hard to tell exactly because we only really see it projected onto the sky. It's hard to tell what the 3D structure is, but yeah, kind of towards the center. But what was interesting is that we've got less zinc, copper, silicon, calcium, and a handful of other metals that were tested as well.
So, I mean, those specific details aside, the point being it's different. Out of the 11 that they were looking at, this one's not like the others. It's significantly different in those various ways.
Well, it's the same in terms of what it looks like. If you just sort of took a picture of it on the sky and said, yeah, that's cool, that's a globular cluster, you'd think it was the same as all the others.
Sure.
It's only when you look at those metals that you start to say, hang on a minute.
So what is this thing, you would ask yourself?
Yeah. Exactly. Okay. So looking at then this whole globular cluster is consistently depleted in metals across all of the metals that they tested. And this is very interesting because it suggests that this globular cluster was formed in a very different environment to the formation of even all the other globular clusters in the Large Magellanic Cloud.
Right, which suggests it's formed in a different environment, a different place, different time. It's come from somewhere else.
Yeah, which means that if you sort of think about this is really metal poor by this point, which means it's probably come from a really small galaxy with not a lot of kind of stellar evolution that's been able to happen. It's probably formed quite slowly as well, which leads us to the conclusion that, well, neither of those things are the Large Magellanic Cloud.
Right.
So sometime in the past, probably a few billion years ago, the Large Magellanic Cloud has cannibalized this galaxy, small, sort of faint galaxy, and it's just absorbed it all.
So that's, I mean, it's really cool off the bat, but it does then start leading me to ask a whole bunch of other questions, like if the Large Magellanic Cloud, like it's large by the standards of the galaxies which are, you know, going around our big galaxy, the Milky Way, but this must have been significantly smaller than the Large Magellanic Cloud to have been sort of cannibalized without, you know, completely messing with everything entirely. So how small can you have it to still be a galaxy? How small do we think this thing was?
Well, we don't really know.
Right.
We know it's obviously smaller than the LMC, probably quite a lot smaller given that we've only found one globular cluster that seems to be out of place so far. It could have been what we call this kind of population of newly discovered and newly characterized population of satellite galaxies called UFDs.
UFD standing for?
Ultra faint dwarf galaxies.
Nice. Okay.
Some of these have only recently been discovered through like the Gaia survey. And these are sort of, we expect the Large Magellanic Cloud itself to have somewhere kind of around 4 to 6 of these as satellites to it, if that makes sense. So,
yeah.
So the Milky Way has a satellite, the LMC, and the LMC has its own satellites, which are these UFDs. And these are kind of the faintest, the smallest, and interestingly, the oldest and most dark matter dominated satellites that we have.
Right.
So the galaxy.
Why is that the case? Why would really small also correspond to like really old, really faint, and really dark matter rich? Like, can we pull any of those threads and figure that one out, or is it just that's what they are?
Well, we can, because this is starting to tell us a lot more about how galaxies actually form.
Right.
So for a long time, there's been a lot of debate about how do galaxies form, and there's two basic ways that you can go about constructing a formation theory.
How to build a galaxy, 101.
Yeah.
Yep.
Yeah. What would you guess,
I don't know. I mean, I have the same mental image of galaxy formation that I have of formation of pretty much anything else in the universe, which is bunch of matter collapses down because of gravity and forms stuff. Beyond that, not a lot of nuance in my understanding of these things. So,
that very basic model is effectively what we call the top-down formation of galaxies.
Yeah.
So top-down meaning you start off at the biggest scales. So after the Big Bang, there's lots of gas and dust and stuff in the universe. Some of that collapsed, and then you had galaxies. Right.
Makes sense.
It does make sense because that's how, like you say, a lot of other things form. That's how stars effectively form.
Big dust cloud, bit of extra density here, collapse down and build up, eventually star.
Yeah. So the opposite model to that, if you like, would be what we call bottom up.
Sure. That again makes sense. Top down, bottom up.
Yep. So bottom up theory states that you kind of make small structures first, and those small structures merge until we get much larger objects of the galaxies that we see around us today.
Right. Weren't we talking about this a while ago in terms of planets? Aren't there various different ways that planets can form? Can't you have things collapsing down to form planets of one kind, but then other kinds of planets form by small chunks glomming together and building up and building up and building up?
Effectively, yeah. So the terrestrial planets, for example,
Yeah.
they are formed by accretion, so lots of small things sticking together. In terms of our planets, the giant ones, kind of the same, except they just grabbed a whole lot of hydrogen and helium as well. But
Right.
yeah, so they sort of work opposite to stars, which is
Right.
quite interesting.
Sure. Okay.
Yeah, so we got this bottom-up idea, and we've been leaning. I'm going to get in trouble here because there is still a lot of debate in the galaxy community about.
Well, I mean, let's put a big
formation models.
asterisk on this and say it is thought that by some astronomers it could be the case that
Well, some of the evidence is pointing more towards the bottom-up theory of formation. And that's been coming out for a while. One of the ways that we have been looking at that has been basically just by looking in the deep universe, because the further away you look from our own galaxy, the further back in time. So the idea, I mean, it would be great if we could just kind of look to the very early first galaxies and say, oh, there's the first ones.
Yeah,
we can see them
watching
forming.
it in formation, easy, but you can't.
It doesn't really work
Can't
like
really
that.
do that?
You know, and especially when we're looking for things that are very, very tiny, very faint. And then, of course, they're very far away.
Yeah, it's already far enough away as it is. You're going to look for the tiny, faint ones too? That's not going to work. Like when you're looking that far away, you can only really see the really bright ones,
Yeah,
I'm guessing?
exactly.
Okay,
Yeah.
so what can you find out then by looking so far away?
Well, I guess more looking into the middle distance,
Right,
if you
okay.
like. We can see that on average, galaxies used to be smaller than they are sort of in the universe around us today. So if used to be smaller and now they're bigger, there's some kind of, I guess, corollary evidence.
Sure. If the ones in the middle distance are smaller, then stretching that out further, really, really far away, in other words, really long ago in time, continue that extrapolation, they're even smaller. So the old ones may be small.
Yeah.
Sure.
And then we've got some other interesting evidence, which has been around for a while and is everyone gets very, very nervous when I start talking about this particular discovery. Well,
All right. Well, I'll brace myself. Go on.
So we've known about globular clusters for a long time. They've been studied for 100 years more.
Okay.
And we've even been able to measure the ages of globular clusters for a very, very long time. So it turns out that a lot of globular clusters in the Milky Way, I've told you that they're old.
Yeah.
I haven't quite told you how old these things are.
Right.
Most of them are as old, if not older than the galaxy.
Okay, hang on. Let me just pull that one apart. We have a galaxy which contains globular clusters. And you're telling me that the globular clusters inside our galaxy are as old as, or even older than, our actual galaxy, which sounds like a paradox. So...
Well, it gets worse.
Yeah.
Some of them are older than the universe.
That's... No.
I told you people get upset.
I'm sorry. I'm going to draw a line here. I can cope with them being older than the galaxy because the galaxy had to form at some point and maybe it captured a few. You can't be older than the universe by definition. So what's going on, Emily?
Well, exactly. That just puts it into context how old these things are. We're
Right.
really talking about the very earliest things that
So within error bounds, what you're basically saying is we're about some of the oldest things that you could get in the universe. We're not actually saying they're older than the universe, just that we can't nail that down necessarily any further than they're really old.
Yeah, and they actually put constraints on how old the universe is.
Right.
Because we know that they actually can't be older than these globular clusters, which I think is quite
unless there's
fascinating,
something
isn't it?
really fundamental we don't yet get about the universe itself. But let's leave that aside for the cosmologist to work out. For the point of view of this one, we've got globular clusters, which are really old. Some of the oldest things that there are.
Yeah.
Okay.
And I really like it because you sort of think if you want to find out the age of the universe, you need to go become a cosmologist and go study, the Big Bang and all this kind of
cosmic microwave background and stuff like that.
all this really old stuff. Or you can kind of just go and study some of the globular clusters that are in our own local.
Just go and look at a bunch of stars. You'll figure it out. Yeah. So does that kind of imply then, Emily? Let me pull this apart. We've got the Large Magellanic Cloud, and we've looked at a bunch of globular clusters in the Large Magellanic Cloud, and one of them is different from the others. And so the interpretation there is, well, it must have been eaten, right? There must have been something else, another even smaller galaxy that got gobbled up, right? If you're then saying within the Milky Way, we've got a bunch of globular clusters, which themselves are really old, maybe even older than the galaxy itself, is it possible that the earliest evolutionary stages of galaxy-type things being, bunches of stars stuck together with gravity, that's sort of the globular cluster level. And then if you start whacking those together, you get what we now know as galaxies? Is that too naive a way of
Well,
looking
I think
at
there's a few steps probably in between, but certainly...
I thought I'd solved it there.
Yeah, but certainly globular clusters seem to be really an important part of how galaxies assemble.
Right. But it's not as simple as just Lego bricks, globular clusters, whack them together, get the Milky Way.
No, sadly. No, because otherwise all we would have would be globular clusters.
It'd just be a big globular cluster.
Yeah.
I can see the flaw in my argument.
I think they're just structures that are very, very good at survival is really one of the useful things. Because they're so dense and they've got so many stars, they're very tightly gravitationally bound. Because what you could ask is say, well, okay, the Large Magellanic Cloud has swallowed this other galaxy at some point. But this other galaxy was bigger than just one globular cluster.
Right.
It would have had loads of stars and maybe even some gas and dust and whatever else galaxies like to have in them. So where's all that gone?
Where's it gone? Yeah.
Well, it's in the Large Magellanic Cloud. We just can't distinguish it. Because how can you say, you star over there, you're from that origin, you star over there.
Right. Yeah. There's nothing that singles them out. But when you've got a globular cluster, which, as you say, is itself, it's a unit in a sense. It's well defined as it's a nice tight little bundle, and that's a pretty stable little bundle.
Absolutely, yeah.
So that can be like no individual star, but that glob of stars, that's distinguishable, and we can tell that that's different.
Exactly. Yeah. Whereas all the other stars sort of got stripped off, got dispersed throughout the galaxy. I mean, many of them will have finished their life cycles also by this point, right? So, yeah, globular clusters are useful kind of relics, if you like, from their previous host galaxies.
It's interesting. I mean, they must be really quite tightly bound, because I've seen simulations of galaxies colliding, and maybe we can get into this a little bit later on. But I mean, these can be quite disruptive events. You can have stuff being flung all over the place. So to have a globular cluster, remaining intact, they must be quite compact and tightly bound.
Yeah, well, I mean, when we think about the core of a globular cluster, this is some exciting stats for you. So, if we think about how dense is dense, I'm being very vague here, right? Let's put some numbers to it.
Okay.
So, if we talk about the inner parsec, so a parsec is about 3 light years or so, and a parsec, if you imagine a sphere, that's a parsec in radius, right?
And just to put some context on that, how many parsecs to the next star?
Basically one.
One. Okay. So we're talking the distance between stars.
Yeah.
Roughly. Yeah.
So the distance from us to Proxima Centauri, roughly, make that a sphere.
Okay.
Do you want to guess how many stars you want to put in there?
Oh, geez. I mean, you're saying this is compact, so I'm going to guess lots, but I have no idea. Like dozens?
It's a minimum of hundreds.
Wow.
Possibly up to 1,000.
In the space of like the sphere centered on us out to the next star, there's hundreds.
Yeah.
1,000.
Yeah.
That's really dense.
It's really, really dense.
Like it must be really bright in there.
Oh yeah. Can you imagine?
Wow.
You'd never have any sort of kind of nighttime.
No. That's amazing. Wow.
Yeah. Exciting. So that's what we're talking about when we talk about dense. So the gravitational binding is really strong.
Yeah. Okay. So that makes sense. Yeah.
It behaves like an individual star, really, rather than a loose cluster where it could be torn apart.
Right. Which makes sense when you think about then when galaxies collide. I mean, it's tempting to think of that as like a car crash and two very solid things hitting each other. But galaxies aren't solid, Emily. There's a lot of space in a galaxy. And so I can imagine something like a closely bound glob of stars remaining intact, even though overall the galaxies might be very disrupted as they merge. These individual blobs actually retain their blobbiness because it's so dense.
Even if you took the largest galaxies and smashed them together, the chances of individual stars colliding is almost none.
Yeah.
It's quite a mind-blowing thing, isn't it?
Crazy. Absolutely crazy. Cool. Anyway, so you were saying that these are very old structures in the universe, older than even the galaxy themselves. Yeah. Mm-hmm. So what are we finding out then from this study? What are we learning?
So we're trying to put together this puzzle of how galaxies form. Now, we know globular clusters weren't the first things to form in the universe because they're actually themselves, they've got metals in them, right? So this puts them in a class of stars we call population 2.
Okay.
Now, confusingly, populations in astronomy work the opposite way to how you might expect chronologically.
So it doesn't start with 1 and then goes to 2 and goes to 3?
No, it goes the other way around.
No. Is population 1 what we see around us now?
That's now.
Ah, okay.
Yep.
Then population 2 is what came before that, and
Yep.
population 3. So you're working your way up in numbers, back in time.
Yeah.
Okay. Well, I can deal with that.
And it's not kind of, it's not a simple generation 1, generation 2, generation 3. It's just kind of broad categories of age.
Okay.
So population 2 are the globular clusters. So they're old, but they weren't the very first stars to form.
Because they've got metals in them, which means those metals had to come from somewhere, and the only place they could have come from was stars that existed previously.
Yeah.
Right.
So we do have an idea of population 3 stars, which are the very first stars that formed in the universe. We haven't found any.
Okay. And we're only going back to 3.
Yeah.
It's weird, isn't it? I kind of feel like the universe is just effectively infinitely old, and yet 3 is not a big number.
Well, life cycles of stars can take a while to get through, right? I mean, okay, the biggest, brightest stars will only last for a few million years, which is not long. But, stars like the sun last 10 billion years, which is...
And that's the age of the universe, give or take.
Yeah.
Right? 13.8, is that the latest?
Yeah.
13.8, which is a really, really long time, but not when you consider the life cycle of stars like our sun.
Yeah.
So it's one of those weird things where it feels like the universe has been around forever, and it actually really hasn't.
So even if a star was born very, very early on in the universe, if it was small enough, which small stars hang around for longer, if it was only about 80% the mass of the sun, then it would still be alive today.
Right. But you said a second ago, we've never seen one.
But we haven't found any.
How would we know? Would it be because it doesn't have anything in it that would have to come from that generation of stars having died? It's just hydrogen, helium, and a little bit of lithium.
Yeah.
Right.
We don't really know what that would look like, and it's unlikely that we'd find it anyway. But, especially because we are very uncertain whether those very small stars would have formed in the very first generation anyway.
Right. It might all have been really, really big ones, which have all gone.
Yeah.
Okay.
I think most theories state that really you build even bigger stars than our biggest stars that we have in the galaxy around us today.
Right.
Because you've got only very basic ingredients, the hydrogen, helium, tiny bit of lithium.
So it's not impossible, but feels unlikely.
Yeah,
Okay.
yeah. And also because of the way that those stars contracted, they seem to have contracted very, very quickly out of the kind of leftover stuff from the Big Bang. Probably a lot of influence from dark matter at this point as well. So all that suggests that you're building bigger stars rather than smaller ones.
Right. Okay.
So those sort of stars all kind of happened. And then at some point, and probably dark matter had quite a big role in this second point as well, we had that kind of next generation which formed globular clusters, probably inside slightly larger structures. Maybe, anyway. And this is where the UFDs come back.
The UFDs, remind me, ultra
Faint
dwarf galaxies. Yeah, okay.
So objects that are kind of, you're looking at, I don't know, maybe like 1,000th the size of the Milky Way. Not very bright today, which is not very, categorizing anyway. But they're very old, and they've got some collection of stars. They might have formed relatively quickly, again, because of dark matter's kind of tug, and the underlying structure basically of the universe was set by the dark matter structure.
Right.
So they might have sort of formed first, which would then explain kind of the origins of this NGC 2005 coming in one of these very early galaxies. And then things just kind of built up from there. So smaller dwarf galaxies like the Large Magellanic Cloud absorbed them. The Large Magellanic Cloud, we haven't even mentioned the Small Magellanic Cloud.
No, I mean, the Large Magellanic Cloud does kind of imply something else.
Yeah.
Otherwise, it's just the Magellanic Cloud. So there's another one, smaller.
Yeah. So it itself is part of, I guess you can almost think about it as a binary galaxy. It's not really in this kind of binary sort of star sense, but they're two very closely linked dwarf galaxies, irregular galaxies of satellites of the Milky Way. They're even connected by a kind of a bridge of stars. Now, what's really interesting about these is that, I guess in contrast to how you might think of a really old galaxy, if it was on its own, an old galaxy, you expect it to kind of be a bit dead.
Okay.
Right? You'd expect it to kind of used up most of its gas and dust, and that would all be locked away in the stars. It wouldn't be doing kind of anything particularly exciting.
Nothing terribly interesting going on.
But the Large Magellanic Cloud and even the Small Magellanic Cloud are actually not like that. They are quite active places.
Active in what sense?
Forming lots of stars.
Okay.
Yeah, so they're quite interesting places. The Large Magellanic Cloud actually has the Tarantula Nebula in it.
Oh yes, I've seen. Okay,
You might have seen
have a
that.
look at your phone right now. It'll have a picture of the Tarantula Nebula on it.
Yeah, it's a lovely nebula to look at. It's one of the most active star-forming regions we have in our whole group of galaxies.
Wow. Okay, so this is far from dead. This is very much alive.
Yeah, and so what's happening now is that the Large Magellanic Cloud and the Small Magellanic Cloud are tidally kind of interacting. And when you get that interaction, you're dumping energy into the system. You're compressing clouds of gas and dust at a faster kind of rate than normal, and therefore building more stars.
Right. Okay. So whereas if they were separate things, you would expect them to perhaps be sort of a bit dead and lifeless. The fact that they are connected is doing that, or is this implying that there's just more going on anyway than we would have ordinarily expected?
I guess it's a bit of both. They're connected, and that's definitely a huge part of their star formation. But they're also kind of connected to the Milky Way.
Yeah.
Right?
Right.
So the Milky Way has a lot of gravitational influence. In fact, I think it's only in kind of a few billion years we expect the Large Magellanic Cloud to be merged into the Milky Way
Right.
itself.
So we're going to gobble that one up.
Yeah.
Which means we'll have gobbled up a galaxy which has gobbled up a galaxy.
Yeah, it's like Russian dolls, isn't it? Yeah.
It's all very confusing. But what it does kind of point out, I guess, is this image of, the cosmic, ladder of scale, if you like, of sort of, stars and solar systems and galaxies and clusters of galaxies. It's much more complicated than that. That our local set of galaxies, our local area, backyard, is a really complicated place.
Yeah.
With galaxies on all sorts of scales and all sorts of age ranges, gobbling each other up, and over time. So what's the long-term view of our local cluster then? Is it all going to just be eaten up by and just become one big galaxy?
Well, sort of. I mean, the Milky Way is good at eating other galaxies.
Because it's so big?
Yeah, we're the most dominant thing
Right.
around us, and we've got all these lovely little satellites that follow around. So we'll eat things that are the size of the Large Magellanic Cloud, and there's some really good evidence we've done that quite a few times in the past. There's been some new stuff come out of Gaia. There's a galaxy that we think we ate that we've given a name posthumously, shall we say?
That's nice.
Called Gaia Enceladus. And that was a galaxy that was just a bit bigger than the Milky Way, but we've sort of been able to figure out that a lot of those stars kind of got dispersed into the halo of our own galaxy. And that's probably something that happens a lot for big spiral galaxies. They probably do a lot of that sort of scale of cannibalism.
Right.
We do it on other scales as well. We do it for very tiny galaxies. We just, pop them down the throat.
Don't even notice.
Yeah.
Don't even notice. It's like all those spiders apparently one is meant to eat in one's lifetime. You just don't even know.
Yeah.
Don't even know.
A great example of that is Omega Centauri, which is we thought it was a globular cluster. Actually, it's a very dense, compact cluster of stars. But the kind of location of it and some of the ways that its metallicity behaves actually suggest it might be the core of a tiny galaxy that we've eaten ourselves.
So in that sense, that's very much like what we've seen in this study here, that we can see another structure which ain't like what's around it. And so that's presumably what's left over from when we ate something else.
Yeah, it's almost like we skipped the Large Magellanic Cloud step and just ate the tiny galaxy that was around beforehand. Yeah, so, we've been doing this for a while, so I'm sorry that Milky Way is not, pure and...
Mind your manners, Milky Way.
Yeah, well behaved. But then if we go to the future, so that's going to continue happening. We've got lots of satellite galaxies. The Large Magellanic Cloud will eat more, then we'll eat it, and then we'll eat, whatever else we can find. But the exciting bit is there is another big galaxy in our region, in our local group.
Yeah, and Andromeda?
Andromeda, yeah. And we've talked about before, Milky Way and Andromeda on a collision course.
Yeah.
Something,
this is going to happen, isn't it?
Yeah, 4.5 to 5 billion years from now.
Which, look, it's not a long time. We won't be around, you and I, but it's on the scale we were just talking before about, individual stars having lifespans longer than that. So, it's not astronomically ludicrous amounts of time. And Andromeda's big.
Yeah, it's bigger than us.
It's bigger than us.
Yeah.
So that'll be interesting. What happens then?
Well, rather than sort of think about cannibalism, where one was going to eat the other and then it just become kind of enormous, there's some models that suggest you might get some kind of super spiral galaxy. But by and large, that's not what we expect to happen.
It's not just going to be these things just sort of merging together like two water droplets sort of sliding together and becoming one big water droplet. It doesn't really work like that. So this could be quite sort of cosmically violent.
Oh, hugely violent, right? So you've got two enormous masses coming together, both of which have a lot of gas and dust still around in their galaxies. So all that will be compressed, squeezed. You'll get star formation. You'll get supernova going off all the time. That's
going to be fun.
Yeah, and then you've got the two black holes, supermassive black holes that are in the center that are eventually going to coalesce, and that's going to be an enormous event.
Yeah, I mean, if Lido's still around at that point, they'll see one hell of a bang from that.
Yeah.
That'll be fun.
It's huge. So what we expect to eventually settle down once Milkdromeda is created.
They just so need a much better word than that. I'm sorry. We need a committee.
Milkdromeda, it works. It saves me having to remember a new name, to be quite honest with you. So Milkdromeda probably won't look like a grand spiral galaxy like Andromeda and the Milky Way currently look like. It will probably be a giant elliptical galaxy.
Okay. Just because the coming together will be just so messy, it'll get rid of all the structure.
Yeah, it's so disruptive to the spiral arms, etc., that it just
they've taken a long time to form and do their thing, and this is going to mess all that up.
Basically, yeah. And this is what we see in a lot of other galactic clusters and groups, is that often in the center you've got this kind of giant elliptical galaxy, which is presumably other galaxies that have come to the same fate.
Okay.
Yeah, and so eventually then what happens after that is kind of a little bit sad, because once you lose your massive neighbor, we don't have a lot of any big other neighbors in our region. We've got another little kind of triangulum galaxy, but it's pretty small.
Yeah. On the scale of this kind of collision, it's not much.
It's nothing compared to
let's just discount that one.
But so then basically you just start running the clock down. So the gas and dust that you have, you can push into star formation when you have the merger event. But after that, there's not a lot of new dynamics that's going to come along.
Yeah. So you just work your way through your stars.
Yeah, exactly. Yeah. So we often call elliptical galaxies red and dead.
Oh, that's a bit sad.
Dead because they're not forming stars, or at least not significant numbers of stars. And red because the big, hot, bright blue stars burn through their lifetimes very quickly. So you're only left with the red stars at the end.
And then eventually you're just left with dead.
Yeah.
Well, that's rather depressing way to finish that particular story. All right, so can we bring it back around then to the topic of today, right? Which is leaving behind Milkdromeda, or whatever the hell you want to call it, in the distant future and red and dead. Back to where we are now, which is seeing the Large Magellanic Cloud, which had, we had a look at 11 different globular clusters, one of which was not like the other. And hey, it looks like the Large Magellanic Cloud ate a much smaller thing, which was very old in the past, and we can tell that. And presumably, the whole point of this is, well, this is giving us just more data, more that we can feed into our models and our theories about how does all of this evolve? How does all of this work? So where does this sort of leave us at the end of today's episode, Emily? What do we know now?
So I think we know that, we've got more evidence to say that the bottom-up theory of galaxy formation is the way to go forward. And that works with our favourite models of cosmology, the Lambda CDM model. Mostly, right. Kind of.
Okay.
I can't say it works perfectly. We do have some real problems in galaxy formation. We have a lot of problems forming enough like big spirals like the Milky Way and Andromeda. So we can't quite match the theory to what we see today yet. But it's almost like we're putting another tiny little piece in that very, very large, millions of pieces jigsaw puzzle.
I mean, how much of that uncertainty around putting that big jigsaw puzzle together is facts like we still don't even know what dark matter is, like that kind of thing. You've got a large part of this puzzle which involves pieces which don't have any picture on them. Where does that go? Like, I can't even imagine how you would come up with a cohesive model when you don't even know what the vast majority of the stuff actually is.
It's incredibly surprising, isn't it? You think we actually know quite a lot about things like star formation, but when it comes to galaxy formation, I mean, really, everywhere I go, it's very hand-wavy and basically what I've just said.
And is that part of the problem? That at that level, like at the level of stars, dark matter, not quite so important. But at the level of galaxies and above, dark matter is really important. Like, that's how we know it's there. And without a solid understanding of that and presumably other things, there's just huge question marks over the top of everything that you're hoping for studies like this to come along and just whack another puzzle piece down. Yeah, fantastic. It's got a picture on it. Put that one there. That one fits. Excellent. Like, is that the issue?
Partially. I mean, we do know a lot about how dark matter behaves,
Sure.
at least sort of locally. And it seems like it's very clear that you needed to have this dark matter structure underpinning the very early universe. But how that influenced the earliest stars and therefore the galaxies, etc., I think that's a question mark that will be helpful to know what dark matter is. But I think we need even more than that, to be honest. I think we need quite a lot more information, and I'm not 100% sure where it's all going to come from, to be honest, but that's probably because I'm not a galactic astronomer who will be able to list off all the exciting new things. But it just shows even just missions like Gaia, what interesting stuff we can pull out from just looking at our own Milky Way and even just looking at our nearest neighbours.
Well, that pretty much does it for today's episode. Emily, thank you as ever for blowing my mind with the scale and capacity of our knowledge about the universe, but at the same time bringing it back around at the end there too. There's just so much we don't understand, and being able to put just one little puzzle piece. Like, that's the nice thing about this story, is it's one little part of one modest-sized galaxy going around one large galaxy, and we can put that little puzzle piece in that says, that globular cluster there, we reckon we know where that came from. Great, fantastic. Everyone come gather around, let's get a photo. Like, that's kind of cool. I like that.
That's how science works, right?
Yeah.
I mean, everyone's sort of beavering away on their very sort of narrow, very small little field, really, when you look at the large scale of things. And so every little tiny little piece of research that we do, it's nice to know that it's got some bigger context.
Yeah. A vast majority of science is about the tiny little puzzle pieces, and then occasionally someone or a group of people come along and go, do you know what? I think I've figured out what this bit of the picture is. You know what you're looking at up in that corner.
But as a squirrel.
It's a squirrel. Yeah, I like that. Well, listen, if you want to get in touch with us and tell us what you think the picture of the universe looks like on the big jigsaw puzzle of the universe, then you can get in touch with us in a whole bunch of different ways. Emily, name one of them. How can someone get in touch?
On Twitter.
On the Twitter.
At SyzygyPod, SYZYGYPOD.
That's not the only place we have that name, though. We have it in at least one other. What is it? Instagram. Well done. We're on the Instagram. We put up pictures and interesting links and so on. We're also on the Facebooks. Not SyzygyPod, but Syzygy Podcast. Put it into the search thing up the top and you'll go and find us. We also have a website.
Yeah.
Syzygy.
Linking all those things as well.
Yeah, syzygy.fm. So go and find us on there, and you can send us a hello through that one as well and find all the past episodes and catch up on anything that you've missed. Listen, if you want to support the show, there's a bunch of ways you can do that. The best way that you can do it is tell everyone you know that there is this thing. It's called the Syzygy Podcast, and if you're a space nut, or even if not, you might enjoy it. So point people towards it. You can give us a review, give us some stars on your podcast listener of choice. Tell the world what you think of us, and it helps us to rise up through the noise, because there's a lot of podcasts out there. I don't know if you've noticed. Help us to rise up through that so that other people can find us. And lastly, you can go to patreon.com and become a patron of the show by throwing us £1, a couple of dollars, whatever you like, every once in a while to help us keep the electrons flowing and help us to do things like live shows when we're able to do that sort of thing again. So that's patreon.com/SyzygyPod. There, that is again. But otherwise, you can just keep tuning in and listening and being out there on the other end of the, I was about to say the airwaves. That's not how podcasts work. The other end of the electrons. Anyway, all of that aside, we'll be back again in roughly a week or so, back in this fabulous new schedule that we've got going, Emily. So until then, I'll catch you later, Emily.
See you later.
Bye, everybody.
point, you do know this is an audio format media,
Why?
right?
What did I say?
Well, no, you do a lot of hand stuff.
I know, but that's how I talk.
Yeah.
That's
But
how I talk.
I think, funnily enough, you do the same hand stuff every week.
Yeah.
The rising.
Rising. Yeah. Well, I mean, it helps to get the, it's an Italian thing. I'm not Italian.